This video we're going to look at cycloalkanes. So cycloalkanes are ring structures. They don't have double bonds or triple bonds, so they're still considered saturated, but they are a little bit different because they form a ring. So when it's a ring structure is going to be less two hydrogens. Essentially our idea for ring structures is if straight chain aliphatics are CnH2n plus 2, if I looked at the ring structure for cyclobutane has 4 carbons, so it's C4, but then if I count up the hydrogens, it's H8. And so you can see that this pattern does not follow this pattern. Well, essentially, every time you have a ring structure, it costs every time you make an extra carbon-to-carbon bond, it costs 2 hydrogens. So instead of it being CnH2n plus 2, as soon as you get that extra carbon-to-carbon bond, it's going to be minus 2, or in this case, CnH2n. There's a little bit of an organization I'd just like to go over at this point. We're studying organic molecules, and we know that it could be organic or it could be inorganic, and you need to be able to tell the two apart. The inorganic examples we mentioned in our first video in this section. Organic molecules can be then further organized into aliphatic or aromatic. And the aromatics we'll talk about in a little while, but aliphatics include both saturated and unsaturated variations. Saturated aliphatics are going to be alkanes, and they only have the single bond. Unsaturated aliphatics are going to be alkenes and alkynes, which we will talk about later, and they have multiple bonds, so double or triple bonds. So we're still talking in this little bit about saturated alkanes, but now they're cyclic ring structures. The cyclobutane can be shown with the 3 different ways of drawing it. So we've got the structural diagram, condensed structural, and line structural diagram. If we were going to do the same sort of work for cyclopentane, it's going to have 5 carbons, and it's going to be a ring structure. And because each of the carbons has already got 2 bonds, each of them can only carry or bond to 2 hydrogens to make it saturated. So it's going to be CH2 in a ring, and we are left with the molecular formula of C5H10. If you get a branch coming off of your ring structure, we're going to not need to assign a number to the branch as long as there's only one branch. So in this case, we've got a cyclobutane with a methyl. So it's just methyl cyclobutane. We're assuming that that branch is coming off of the first carbon. So our general principle for naming organic molecules is not to give numbers to things that don't need them. In this case, since there's only one branch and it's a ring, it's going to be at the first carbon. But if we had 2 branches, we're going to have a methyl on 2 different carbons. This one needs to get numbered. So it's going to be a cyclohexane because it's got 6 hydrogens, right? It's got the 1, 2, 3, 4, 5, 6 hydrogens. And then it's got methyls coming off 2 of them. We need to give these lowest number order possible, so we'll go with 1, 2. If we counted the other way, it'll be the same, right? It'll be just 1, 2. But what we would not do is we would not go 1, 2, 3, 4, 5, 6. That gives us a larger branching number. So this is going to be a 1, 2 dimethyl cyclohexane. And if we wanted to calculate out the number of carbons or get its molecular formula, you can see that there are 8 carbons, right? There are the 6 in the ring and then the 2 in the branches. And because there's If it was a straight chain or branched alkane, it'd be C8H16 plus 2 would be 18. But because this has got this extra carbon-to-carbon bond that is closing the ring, it's actually C8H16. And it doesn't matter that these are branches. We can still apply the same principle for coming up with a molecular formula. We're going to stop there, and we'll start the next topic will be unsaturated aliphatic molecules. That'll be the next one.